Thank you, everyone, for joining this webinar. I'm excited to be here to present to you today. So let's get started on the presentation. So in today's webinar, we are going to cover an introduction into the multi-point low-voltage differential signaling technology, or M-LVDS, what it is, and some of its advantages over ORS-45, some applications where M-LVDS transceivers are particularly suited, and then we will dive into the M-LVDS portfolio that is offered by analog devices, including some new and upcoming. Finally, we're going to cover some technical details of how and why you would isolate an M-LVDS interface, and some tips, tricks, and common pitfalls to avoid when designing a high-speed backplane using M-LVDS. So first we will cover an introduction into the M-LVDS technology. So M-LVDS stands for Multipoint Low Voltage Differential Signaling. It's a physical layer standard that was released in 2002 by the Telecommunications Industry Association and the Electronic Industries Association under TIA-EIA 899-A. It's designed specifically for high-speed communication at several hundred megabits per second between multiple nodes on a single differential cable or backplane. It extends the performance of the commonly used LVDS standard to include the capability for multi-point communication. This is done through two ways: by adding an increased drive strength to the transceiver and extending the common mode range. Today's M-LVDS transceivers can support up to 250 megabits per second, with a theoretical max in the standard of up to 500 megabits per second. It's also a relatively low power interface and maintains the strong noise immunity of LVDS technology. One of the main advantages of M-LVDS is the data rate that it delivers. Here, a number of interfaces are shown versus their data rate. For example, peripheral interfaces such as ORS-232 and USB. For fieldbus and communication over long cables, ORS-45 and CAN are common and powerful solutions for data rates up to 50 megabits per second, but they struggle to deliver higher bandwidths. Industrial Ethernet, operating at 100 megabits per second and 1 gigabits per second, does support higher data rates, but they lack the support for multi-point communication over a single medium. M-LVDS delivers the high data rates of up to 250 megabits over a multi-point network, which is well suited to these short cables and backplanes. It is a flexible and high-speed communication interface, which extends ORS-45 data rate well beyond 50 megabits per second. Communication networks can be configured and set up in various ways. A common topology is the point-to-point link shown here between two devices. Here there is one defined transmitter and one receiving device, and the data flows in one direction only. Multi-drop is another common configuration, where only one device can transmit to multiple receivers along the same cable. The data here still flows in one direction only. The LVDS standard supports both of these cases, but it does not have support for multi-point communication. For example, in this multi-point network, data can flow in either direction. This allows a large number of devices to communicate over the same differential pair. The M-LVDS standard adds support for these multi-point networks, as well as supporting point-to-point and multi-drop. M-LVDS is a low-complexity interface which is flexible and can easily be added to an existing communication link. Here is a standard communication link hooked up between two processor UARTs or FPGAs. This communication is single-ended and is only suitable for short distances and is susceptible to noise. By adding M-LVDS transceivers to the UART or FPGA I/O, the communication link now becomes differential, and it can be used to send data over long distances. The UART or FPGA I/O can drive the drive-enable or receive-enable pins of the transceiver as needed. No dedicated MAC or controller is needed, and a higher-level protocol can be implemented inside the microcontroller or the FPGA. This also allows the use of custom tailored protocols for a particular application. The M-LVDS standard defines only the physical layer of the communication, which is the bottom layer in the Open Standards Interconnect model. This covers the electrical characteristics of the communication only. Concepts like bit encoding, flow control, addressing, and error correction are not defined by the M-LVDS standard and must be included in a higher level communication protocol. There are several communication protocols which either have support for or options for the M-LVDS physical layer. Micro TCA and advanced TCA are backplane communication protocols for use in industrial PCs. The wired trigger box within the LXI specification for instrumentation utilizes the M-LVDS physical layer. OpenVPX is a framework for communication between modules, backplanes, and chassis which has support for M-LVDS. However, the majority of M-LVDS use cases that we see are proprietary protocols developed by the end customers. These can be tailored to a specific use case and may be closed source for many reasons. M-LVDS is seen across various applications, but in particular it's found in backplane or clock distribution systems, in industrial process control, motor control, instrumentation, and communications infrastructure. Here we are showing an example M-LVDS network, which is allowing communication between several devices. When data is sent by a processor on the left, it is converted to M-LVDS signals which are sent to all devices on the network. At the end of the network, another transceiver converts from differential back to standard I/O for the receiving processor. The advantages of this network, which we have discussed, are that it is differential, which is inherently more robust than single-ended communication. It supports high data rates, is capable of communicating with up to 32 devices on a single cable, and it is simple and flexible. The topology shown is a multi-point network. However, M-LVDS can also support point-to-point and multi-drop networks. To support these various topologies, M-LVDS transceivers come in various shapes and sizes. These various form factors for different M-LVDS transceivers are shown here. The devices differ by whether they support full or half duplex networks. Here, a full duplex transceiver is shown, which has separate I/O for the driver and for the receiver. This is useful as it can be used for simultaneous bidirectional communication on a point-to-point or multi-drop network. These are usually available in 14-pin SYC or a 16-pin LFCSP package. The half-duplex transceiver, on the other hand, is designed for use with a single differential pair. Internally, inside the transceiver, the driver and receiver are connected both to the same A and B pins. These A and B pins function as both the inputs and the outputs to and from the network. These devices are available in 8-pin SOIC packages, and they're suitable for multi-drop and point-to-point communication, and also multi-point communication. For applications requiring higher bandwidth, or perhaps a level of redundancy via additional communication lanes, high-density multi-channel transceivers are available. For example, here we are showing a quad-channel half-duplex transceiver in a 7mm by 7mm LFCSP package. We will now look at some of the common applications for the M-LVDS transceiver and the M-LVDS physical layer. As discussed, M-LVDS transceivers have characteristics that are well suited for use in backplanes. This makes them an ideal choice for connectivity within a data acquisition rack. In these racks, sensing, actuation, and communication functions are done via various I/O module cards. The modular backplane architecture leads to a scalable and efficient process control system. It is also well suited to systems designed for condition-based monitoring and asset protection, or for distributed computing systems. A single M-LVDS lane connects up to 32 module cards with a bandwidth of up to 250 megabits per second, while maintaining low power consumption, which helps control the internal chassis temperature. The compact form factor of the latest M-LVDS transceivers from analog devices means this can be scaled with up to multiple lanes for more bandwidth. And M-LVDS transceivers from analog devices are robust against ESD events, and they're designed for live insertion and removal from a powered backplane without damage or any glitches appearing on the bus. An emerging area for M-LVDS is within motor control, as the interface between a controller and several remote devices, such as a positional encoder or a temperature sensor. Traditionally, RS422 and RS485 have been the interface of choice for remote control. However, with the recent need for increasing bandwidth, RS485 is fast approaching its upper limitation in speed. The plot on the bottom left here shows how the data rate requirement for positional encoders has increased over the years, approaching the 50 megabits per second limitation for most RS485 transceivers. M-LVDS, on the other hand, provides a high-speed alternative to RS485-based encoder links, while still maintaining much of the robustness of RS485 communication. It is well suited for short to medium range, high bandwidth encoder links. The increased bandwidth along the encoder link allows for additional sensors or devices on the servo side, for example, a vision sensor. SPI is a very common interface for accessing ADCs, sensors, and for processor-to-processor communication. It works very well over short distances. However, SPI does not scale well to work over longer distances for various reasons. This makes it challenging when attempting to access remote sensors such as an accelerometer or a temperature sensor. The challenges of SPI are it's not designed for use with combination. Therefore, at high clock rates, the cable will act as a transmission line, and you will get reflections which can disrupt communication. SPI is single-ended, which inherently is poor for EMC. Both produces EMI and is also susceptible to external noise. In SPI, there is no tolerance for ground offsets between the processor or a remote sensor, which can cause communication to fail completely. And the cable itself adds propagation delay, which will reduce the timing margin in SPI and limits the maximum clock rate. A simple solution to these issues with SPI is to convert from single-ended SPI to the M-LVDS physical layer. By adding an M-LVDS transceiver to both controller and remote devices, the communication link now becomes a multi-point bus. This bus is correctly terminated, which eliminates all the reflections. The differential nature of M-LVDS is inherently better for EMC. M-LVDS has a wide common mode range, which can tolerate up to ±2 volts of ground offset between the controller and the remote nodes. And the M-LVDS transceivers themselves introduce very little latency to the network. Another advantage is these transceivers, they're usually equipped with very robust I/O that provides good protection against transients in harsh environments. We will now dive into the portfolio of M-LVDS transceivers offered by analog devices. Analog devices' portfolio of LVDS and M-LVDS transceivers are shown on the slide here. The main family of M-LVDS transceivers is the ADN4680E family, which is shown here in the bottom left. Half and full duplex options discussed earlier are available, both with 100 megabits per second and 200 megabits per second speed grades. These are available with two separate receiver types, M-LVDS Type 1 and M-LVDS Type 2. Type 1 receivers are used for maximizing noise margin. Type 2 receivers include support for failsafe should errors occur on the network. The recent releases from analog devices have focused on decreasing the transceiver size to maximize density, with the new ADN4680E and ADN4693E-1 transceivers offering significant improvements in the device footprint. Analog devices also has a family of LVDS transmitters and receivers, which are shown here in the center column of the slide. Most recently, a family of isolated LVDS transceivers has been brought to market, which support 600 megabits per second, 1.1 gigabits per second, and 2.5 gigabits per second. These isolated transceivers are available in 2- and 4-channel options with a variety of channel configurations. The key advantage when using analog devices M-LVDS transceivers is the high levels of ESD protection and general robustness. All devices within ADI's M-LVDS portfolio deliver high levels of ESD protection to the stringent IEC 61000-4-2 standard for ESD. All devices meet Level 4 contact ESD, which is the highest level specified by the standard. This integrated protection is critical in M-LVDS networks. As we're going to see in the coming slides, minimizing capacitance on the network is critical for signal integrity. By integrating DSD protection, no external components are needed to create a robust I/O. These components will otherwise add unwanted capacitance to the bus. It is worth mentioning that the IEC 61000-4-2 standard is significantly harsher test than the traditional human body model test, with 50% more energy and 450% higher peak currents for the same test voltage. Based on this, transceivers with IEC protection, like the M-LVDS portfolio from analog devices, offers a significantly higher level of robustness than transceivers with only HBM protection. In general, devices which connect to the outside world have strict EMC requirements. ADI's M-LVDS transceivers are no exception, but they are well suited to operating in harsh environments. As discussed on the previous slide, they feature high levels of ESD protection. The ESD protection devices used within the M-LVDS transceivers also afford protection against electrical fast transients. Unlike ORS-45 transceivers, M-LVDS transceivers are tested to minimize peak-to-peak COM mode noise, which will minimize EMI generated by COM mode noise on a cable. And the M-LVDS COM mode range provides good immunity to externally generated COM mode noise. This can be further boosted with the use of a COM mode choke. Surge protectors can also be added, so this would typically only be required for cable lengths over 30 meters, which is a small subset of M-LVDS use cases. So when showing the M-LVDS portfolio slide, I mentioned 2 new M-LVDS transceivers from analog devices. These latest transceiver developments have focused on increasing density and smaller device footprints. In the half-duplex family, the latest device has integrated 4 transceivers into a single package, with only a 35% increase over the existing single-channel half-duplex transceiver. This represents a 3x reduction in the area per transceiver. And the temperature range of the device has also been extended. Full duplex products, the size of the single full duplex transceiver has been reduced by a factor of 3.5 by moving from a leaded SOIC package to a leadless LFCSP package. The improved thermal performance of the LFCSP package has also boosted the temperature range of this device. Both devices are shown on screen here, the ADN4680 quad transceiver and the ADN4693E full duplex transceiver. The ADN4680 quad transceiver is 4 half-duplex M-LVDS transceivers in a single 7mm by 7mm LFCSP package. The data rate has been boosted versus the original family, moving from 200 megabits per second to 250 megabits per second. Minimal latency, pulse skew, channel-to-channel skew, and additive jitter maintain good signal integrity at these high data rates. And an extended temperature range of -40°C to 105°C is supported. With these products, we really placed a particular focus on controlling the power consumption. So here, the dynamic power consumption at 250 megabits is 65 milliwatts lower than the competing solutions. This is particularly important in applications where you have more than one of these transceivers. Flexible low power modes are included, where the individual transceivers can be shut down or powered up as needed, which helps further minimize heat dissipation. And as is standard with the ADI M-LVDS portfolio, the I/O includes level 4 contact IEC ESD protection, and the devices are hot swappable for use in backplanes. So when discussing some applications for M-LVDS, we mentioned that M-LVDS is a useful physical layer to solve the problems encountered when you're trying to send a SPI interface over long distances. And I wanted to show here how the ADN4680E device just presented is a very good fit for this application. Because the ADN4680 is a quad transceiver, you can actually convert all 4 signals within SPI to from single-ended to differential M-LVDS using the one device. The fact that each of the transceivers are half duplex means that each transceiver can be individually configured for either transmitting or receiving. So this lets the same device or even the same piece of hardware be used and play the role as either the controller or the peripheral device in a SPI network. So that's shown in the circuit here. The circuit here is a SPI over M-LVDS with a little more technical detail than before, using 2 ADN4680Es, one at each end of the SPI. So the way it's set up here, an I/O pin can select the transceiver to operate as either the controller or the peripheral role in the SPI. The IEC ESD protection of the transceiver is a nice feature when you're extending SPI over long distances, where EMC and transients become a bit more important. The graph on the right shows why the low latency on M-LVDS is an advantage. So in SPI, you have a limited time period of a half clock cycle for the clock edge to reach the peripheral and for the data to come back. And any added latency eats into the budget and can reduce the maximum clock rate allowed in the SPI. M-LVDS has a much lower latency when you compare it to other differential transceivers like RS-45, so it is well suited for extending high SPI clock rates over several meters. So when discussing some applications for M-LVDS, we mentioned that M-LVDS is a very useful physical layer to solve the problems that are encountered when you're trying to send a SPI interface over long distances. And I wanted to show here how the ADN4680E device just presented is a very good fit for this application. And because the ADN4680E is a quad transceiver, you can actually convert all 4 signals within the SPI from single-ended to differential M-LVDS with the one device. The fact that the transceivers are half duplex means that each transceiver can be individually configured for either transmitting or receiving. This lets the same device or even the same piece of hardware be used as either the controller or the peripheral role in a SPI network. So the circuit shown here on the top left is SPI over M-LVDS, with a little bit more technical detail showing how this is done using 2 ADN4680Es, one at each end of the SPI. So the way this is configured here, an I/O device or an I/O pin can select the transceiver to operate in either controller mode or peripheral mode. The IEC ESD protection of the transceiver, it's a nice feature when you're extending SPI over long range, where EMC and transients become a little bit more important. And you know, considering latency, the graph on the right shows why the low latency in an M-LVDS transceiver like the 4680 is an advantage. So in SPI, you have a limited time period of a half clock cycle to get the transmitting clock edge to reach the peripheral and then the returning data to come back to you. And any added latency eats into that budget and can reduce the maximum clock rate that you can use on the SPI reliably. So where M-LVDS has the advantage is that it has much lower latency than other differential transceivers, for example, like RS-45, which is compared in the graph here. So M-LVDS is well suited for extending high SPI clock rates over several meters of space. Here we are showing the latest full duplex transceiver from ADI, the ADN4693E-1, which is currently on pre-release and is available for sampling now. The improvements to this transceiver echo much of what has been presented on the previous slides for the ADN4680E. We've put a focus on minimizing footprint, going 3.5 times smaller into a 4mm by 4mm LFCSP package. the junction temperature of this device has been extended from 85 C up to 120 C. And the leading timing performance and ESD protection from this device family has been maintained with this new release. Similarly, we are showing here some design resources for the new ADN4693E product. While the transceiver has not fully released to production, samples are available now, and a preliminary datasheet and product page are available on the web via the links shown on this slide. An IVUS model is currently available for early simulation and prototyping, and an evaluation board will be available at release towards the end of this year. Next, we're going to cover some tips and tricks for when you're designing an M-LVDS backplane. There are a couple of key concepts when you're designing an M-LVDS backplane. And really the main goal is to maximize the signal integrity on the backplane. So there's four kind of things you can break this down into. The first one is you need to control the backplane impedance. So the backplane impedance, as you move along the backplane, needs to stay relatively constant from module to module. And it's also important that that impedance doesn't drop too low, and we'll discuss that in the coming slides. The second thing is that it's very important that the backplane is correctly terminated. Now there's kind of a common pitfall or common mistake that's made here, which we'll also discuss, but the termination resistors need to be matched to the backplane impedance, which may not be what you think it is. The third thing to consider is the general attenuation on the backplane itself. Now this only really comes into play for larger backplanes or data rates that are on the high end of the M-LVDS spectrum. And the last thing is that you can be particularly careful about the transceiver selection that you can, and we'll discuss a little bit about type 1 versus type 2 receivers and where each of them should be used, and also how the transmitter rise and fall time comes into play when designing a backplane. The first topic to cover is the impedance of the backplane itself. So you can see here on the slide I have a transmission line model. This is the standard RLGC model for a transmission line. And the reason for this is that you can effectively model the backplane and the signal integrity on the backplane. You model the backplane as a transmission line. And the key metric or the key figure of the transmission line is this characteristic impedance. This is Z0. And so anytime we refer to backplane impedance, it's this characteristic impedance that we're referring to. Now, we can take this a step further and we can perform a bit of a simplification, and we can remove the resistive and the conductive terms and assume that this is a lossless transmission line. And this is valid to do because the data rates of M-LVDS extend only up to 250 megabits. So those terms have a minimal impact on characteristic impedance. And so now you can see here the lossless transmission line model with the inductive term and the capacitive term below. And these combine to give the characteristic impedance of the backplane. This is Z0, which is the square root of the inductive term over the capacitive term. And the key thing to remember here, why we care about this backplane impedance, is that any changes in this backplane impedance, or the transmission line impedance, along the backplane will generate reflections. And these reflections will adversely affect your signal integrity. So the goal here is very important to try and maintain a uniform impedance across the transmission line, across the whole backplane, because this will give you good signal integrity and a reliable communication mode. So we're going to lower the difficulty here a little bit, and we're going to first discuss how you would design an LVDS backplane. So this is not a multi-point backplane, but it is just a communication link between two devices. So this is pretty trivial. Since it's a point-to-point interface, at the data rates involved with M-LVDS, maintaining a constant impedance is relatively easy along the trace of the backplane. So you make sure that your PCB traces are uniform and you correctly terminate at either one or both ends of the network. And this will ensure that the Z0 or the characteristic impedance stays constant throughout the whole network, and you get no reflections. Now we'll consider how the same problem would look for designing a multipoint or an M-LVDS backplane. And here you can see the challenge is a lot more difficult because as you move along the backplane, you have a constant impedance. But because this is a multipoint interface, there are multiple module cards lying across the backplane. And each time you encounter one of these module cards, the impedance of the backplane itself will change. And that's because in a multipoint interface, each node that you add is actually a capacitive load. It has a transceiver that has a certain capacitance. There are stubs on the board and PCB traces and possibly protection components. All of this add capacitance, which presents a capacitive load, which is added in parallel to the existing capacitance that's on the backplane. And because of this, maintaining a constant impedance is very challenging in a multi-point network. Now, if we refer back to the equation we had for characteristic impedance, which was Z0 equals the square root of L over C, we can see here that the Z is roughly inversely proportional to the square root of the capacitance. So as we add capacitance to the network, or as we add new module cards, or we add new transceivers, and this will add a new load capacitance, and this will start to decrease the impedance of the backplane. And so this phenomenon of decreasing backplane impedance as you add module cards, this brings me to the main common misconception when designing a backplane. And that is, okay, so I have my backplane traces, and I told my layout engineer to lay them out for 100 ohm differential. Therefore, my backplane impedance is 100 ohms. And that is true, but only while the backplane is unloaded. And so as shown there on the last slide, here's the lossless formula for characteristic impedance. And we can see that Z0 is inversely proportional to the square root of CL. Backplane modules are capacitive loads. So when you add modules, you reduce the impedance at zero. And this raises two important points. A module that has a higher capacitance will result in a lower impedance on the backplane. And also, as you space more modules closer together, the capacitance per unit length starts to increase. So tighter module spacing further reduces the effective backplane impedance. And that's shown on the slide here on the right, where you can see for various capacitive loads, these are approximating module cards with a 5, 10, and 15 picofarad load capacitance. How you can see as you sweep from the left to right, we're starting to decrease the distance between the nodes, so the cards are coming closer together. And this backplane, the PCB traces have been laid out for 100 ohm differential. What we can see as we start to add module cards and bring the modules closer together, we can see the backplane impedance actually starts to drop below 100 ohms. And in fact, taking one example here with a 10 picofarad module that are spaced 5 centimeters apart, Z0 actually halves from 100 ohm, which would be the misconception thinking my backplane is 100 ohm differential. In actual fact, when it's loaded with all the module cards that are 5 centimeters apart, it has actually been reduced to 50 ohms. So the question is, now that we know that the impedance of the backplane may be dropping lower than what we originally expected it to be, the question is, what impact does that, or what effect or negative effect does that have on the signal integrity? And to discuss that, we need to consider termination and correct termination on the backplane. So for an unloaded backplane, let's say characteristic impedance of 100 ohms, the correct way to terminate this is to place termination resistors across the differential pair that match the characteristic impedance of the backplane. So typically, this would, for 100 ohm Z0, you would put RT equal to 100 ohm at both sides of the backplane. So this backplane is unloaded and it's correctly terminated. The challenge comes now when you start to add module cards, and the Z0 drops, say, from 100 ohms to 60 ohms with the added capacitive loads. And the problem now has arisen that this backplane is no longer correctly terminated. We have a backplane that is 60 ohm characteristic impedance, and at the end of the backplanes, we're terminated with 100 ohm. And this 60 to 100 ohm difference is a significant impedance mismatch, and this will generate a lot of signal integrity issues. And you can see here on the slide the reflections that will be generated by the fact that the termination resistor now no longer matches the characteristic impedance. So the solution to this is actually to terminate the backplane not to the characteristic impedance of the traces, but to the characteristic impedance of the fully loaded backplane, or the loaded backplane. So that's here shown on the bottom of the slide. The termination should be matched to the effective impedance of the backplane. And you can find out what that impedance is through hand calculations, or you can do simulations in something like ADS or hyperlinks, or you can measure it using a VNA or a TDR system. And as in a system where you'll be adding and removing, different numbers of cards, the optimum solution may be to choose a termination resistor that strikes a balance between, a very fully loaded backplane and lightly loaded conditions where only, partial number of modules are inserted into the chassis. So I mentioned there at the start that as well as keeping the backplane impedance constant, we should also ensure that the impedance does not drop too low. And the question is, why do we care if the impedance drops too low? Because now on the previous slide we learned that the termination resistors could be matched to the effective impedance, and if we do this we can eliminate reflections. Well, there is a consequence to reducing the termination resistance. So as the backplane impedance lowers, you need to lower the termination resistor at either end of the backplane to maintain good signal integrity. But the negative consequence of this is this reduces the output voltage or the swing out of the transceiver that's seen on the bus. And you can see this on the right in the diagram here. So as Z0 drops from, say, 100 ohm to 70 ohm, you will drop the termination resistors from 100 ohm to 70 ohm. But this has the consequence of actually reducing the output voltage from the transceiver by 150 millivolts. And there's a practical limit to this. If you keep reducing the output voltage, eventually, it's not going to be significant enough for the receiver sensitivity on the backplane. So really what we would strive to do is to keep the backplane impedance as high as possible. And we'll discuss that in the next slide. So we've already seen that the two key parameters that affect the backplane impedance and how much it gets reduced are the capacitance of a module card and the distance between the modules on the network. But there is a powerful tool that we can use to try and offset some of this reduction, and that comes down to the PCB layout itself. So by increasing the differential pair impedance beyond 100 ohms, we can try and counteract some of this reduction that's caused by the addition of module cards. And you can see this in the comparison between the graph on the left and the right. So let's say we take a hypothetical lower limit for our backplane impedance and say we wish it to not fall below 70 ohms. Well, in the case where the differential pair is laid out for 100 ohm differential, you can see that for a 5 picofarad module, and this can be spaced 8 centimeters apart before you reach this 70 ohm impedance. But in the case where the differential pair impedance has been increased to 130 ohm via PCB layout, you can see that you can actually space the module cards almost twice as close together, 3.5 centimeters, before meeting the same 70 ohm impedance. Or another degree of freedom this would give you is to maintain roughly the same separation, but have a module that has a larger capacitance. So this is really the key here, is that by increasing the differential pair impedance, this compensates for the capacitive loading effect of adding modules onto the bus. Now, there is a practical limit that exists for manufacturing PCB traces above 130 ohms. So each PCB house will know what PCB trace impedance they're comfortable with laying out. So just to summarize some of the points discussed for when designing an M-LVDS backplane, the module capacitance and the distance between the nodes reduces backplane impedance below what you may think it is. So you should strive to limit module capacitance where possible, so use short stubs, low capacitance connectors, don't add extra components, and if possible, try and increase the distance between the modules on the backplane. Regarding termination, you should terminate the backplane to the measured impedance of the backplane, not to the PCB trace impedance. And just important to remember that the output voltage will change with the termination used. To try and compensate for some of these loading effects, you should or can lay out the M-LVDS differential pair with a higher impedance than 100 ohm, going as high as 130 ohm. And on the signal loss end, at higher M-LVDS data rates, maybe 200 megabits per second plus, you should start to consider the attenuation of the signal as the backplane length starts to exceed half a meter. Some other considerations that weren't discussed, we'll run through quickly here. Type 2 receivers have less noise margins, so only use Type 2 if it's necessary. Route the differential pair over a continuous plane, as you would normally do in PCB layout. And length match the signals in the differential pair to avoid any mode conversion. And if you're using a low bandwidth or low speed M-LVDS bus, consider using one of the slower transceivers portfolio, which have slower rise and fall times, which are less susceptible to reflectance. Finally, we're going to cover some options for adding galvanic isolation to an M-LVDS network, and why and how you might do this. So the first thing to consider when discussing whether we would not isolate an M-LVDS network is to consider why isolation is needed in communication networks. So typically, isolation is added to communication for one of two reasons. The first one is to remove ground offset or to handle ground offset voltages, which would otherwise cause ground current to flow between various nodes. And this ground offset voltage can disrupt communication or even damage transceivers along the network. So by adding an isolation barrier between the transceiver and, say, the processor or UART, this isolation breaks the ground loop between the two earth references and essentially prevents damage and disruption of communication. The second main reason is for safety. So in systems that may have live electronics and have personnel or sensitive electronics at other points in the network, isolation can be added to help shield this personnel and sensitive electronics from dangerous and hazardous high voltages. Should a fault occur at a remote node and the M-LVDS bus goes live, the personnel and electronics at every other node on the device is safe due to this isolation barrier. Now, how to isolate transceivers with M-LVDS? This can be easily achieved by pairing analog devices, digital isolation technology, with one of the M-LVDS transceivers that was discussed today. And when doing this, there are a couple of isolation specifications to be aware of, and we'll just quickly run through them here. One is the isolation voltage, generally referred to as the ISO. This is an isolated rating for temporary fault of up to 60 seconds during an overvoltage event. The working voltage, or VIOWM, is the rating for a device over the full lifetime of the isolator, typically in excess of 20 years. Creepage and clearance is the distance across the device package between the two isolated grounds. And the common mode transient immunity is a figure of merit for an isolated immunity to noise. So I'm showing here two separate options for isolating an M-LVDS transceiver using analog devices digital isolation technology. So the first one is actually a rather new option available to us. So now that the merger deal has closed with Maxim, I'm delighted to announce that we have access to this high performance digital isolation transceiver here. So this MAX 22445 is a 4-channel digital isolator that's very well suited for use with an M-LVDS transceiver. And that's because it supports data rates of up to 200 megabits, which is paired very well with the data rates that M-LVDS can support. And it does this with adding minimal jitter of about 100 picoseconds typical, and only a max of 2 nanoseconds pulse width distortion. So very high performance single-ended digital isolator here. And the insulation specifications are pretty impressive as well, with 1500 volt VRMS working voltage and 5 kV withstand and 8 millimeters creep-string clearance, which makes it suitable for use in a majority of applications where mains reinforced insulation against mains is required. Now, in certain applications where isolated power is required, there is a more compact option available via this integrated device here. And this is the ADN4680E family. And this is a 4-channel digital isolator integrated with an isolated DC-DC converter. And this is all integrated together in a very compact 28-lead fine-pitch SOIC package. So the coupling of these two devices allows the integrated DC-DC converter that's integrated here can actually supply the 3.3 volt for both the isolation and the 3.3 volt supply that's required for the M-LVDS transceiver. And it does this while meeting the low radiated emissions requirements of a electromagnetic compatibility standard like CISPR 32. The digital isolation core in this product is also relatively low power and supports up to 100 megabits operation to support the majority of data rates that would be used in M-LVDS. And finally, I'd like to cover some of the most recent options for isolating LVDS from analog devices is the option to actually isolate the LVDS physical layer directly. So ADI has a portfolio of very high bandwidth LVDS isolators. They're the fastest on the market. And they are suitable for point-to-point and multi-drop isolation, as shown in the diagram here. However, we did a lot of discussion today about multipoint M-LVDS, and these isolators are not suitable for use in multipoint, just limited to point-to-point and multi-drop applications. And the flagship product of the family here, which just released there last month, is the ADN4680E. And this is a 2.5 gigabits per second quad-channel LVDS isolator. It has 10 gigabits per second total bandwidth, 2.5 gigabits per channel, and it's precision timing for high speed with very low jitter and skew, and fully compliant LVDS inputs and outputs. And so this is just yet another option for isolating either an LVDS or an M-LVDS physical layer. Okay, with that, that will conclude my presentation. I'd like to thank everyone for attending and your time today. Thanks, everyone.